You are watching part 1 of the Control Educational video series, Process Control Basics, Level Measurement. This event is brought to you by our sponsors VEGA, Endress Hauser, and KROHNE. More information about the sponsors will be provided later on in this video. Today's presenter is Editor-in-Chief of Control Global, Paul Studebaker.
You'd think it would be straightforward to measure how much material is in a tank, reactor, or other container. But every vessel and each material has its own set of challenges, and over time, the wide variety of applications have led to a lot of choices of level sensor technologies, each designed to deal cost-effectively with a certain range of parameters. Part of the problem is that level measurement comes second to the primary tasks of mixing, batching, storing, and reacting that take place within vessels. The conditions inside the vessel are determined by a process engineer. For example, a reactor may require high temperatures, high pressures, and vigorous agitation, and the level instrument must be chosen to accommodate those conditions. If the solids in a silo tend to pile up in one place or form a rat hole, there may be no true level to detect. A tank head space, the space above the material, may contain vapors or dusts that obscure the view of the surface, and sometimes the level of interest is actually an interface between two immiscible liquids. Tank contents may include foam that blurs the surface. Foam or fluids may coat, build up, or solidify on the sensor. Fluids may be corrosive or react chemically with sensor materials. Another important consideration is whether absolute accuracy is required or just reproducibility. High absolute accuracy is usually needed for custody transfer. On the other hand, for in-process applications where the target is stability for process control, it's enough that the measurement be precise and repeatable. There are other considerations that often guide engineers to suitable technology. Can the level sensor be inserted into the tank, or must it be completely external? Is a continuous measurement needed, or will a point sensor be enough? Sometimes a discrete level switch will do. Can the sensor come in contact with the process fluid, or must it be located in the vapor space? Is a direct measurement of the level needed, or is it acceptable to measure hydrostatic head, which responds to both level and density changes? Can the tank be depressurized or the process shut down to remove or maintain the sensor? Are the tank contents viscous, sludgy, or foamy, powdery, chunky, or sticky? Level instruments leverage a variety of physical operating principles. Here we show common technologies and applications arrayed along a continuum from the cheap and easy to the expensive and difficult. Each of these technologies comes with its own advantages and disadvantages. We'll revisit this chart as we briefly describe the common technologies. We'll start with the mechanical devices, which lie at the lower end of the cost scale and can handle many of the easier applications. Mechanical float and displacer devices are similar in concept. The tank on the left has a cable-mounted float that is lowered at intervals to detect and measure the level of the surface, then rises up and out of harm's way. On the right, two versions of paddle switches actuate when the level rises to the paddles. Similar point level switches are available using vibration. The presence of surrounding liquids or solids causes a shift in resonant frequency of a vibrating probe. Magnetostrictive level gauges use a float containing a permanent magnet that moves freely up and down a magnetostrictive waveguide. A low current interrogation pulse travels down the waveguide, and when it reaches the float, a torsional twist and reflection are created. The time of reflection indicates the float position and level. Capacitance and admittance gauges can cover a broad range of applications at a reasonable cost. Capacitance and RF admittance devices include both point-level switches and continuous gauges. They detect and measure changes in the electrical properties of the space between two electrodes. In the common application shown here, the electrodes are a long probe and the tank itself. Ultrasonic gauges are also quite versatile and offer good value. Ultrasonic gauges calculate level based on the time required for an ultrasonic signal to be reflected from the liquid surface. They and the other time-of-flight gauges coming later use signal conditioning and computing power to adapt to specific liquids, solids, and vessel conditions. They're seeing increasing applications as the cost of signal conditioning and computing has come down. Differential pressure gauges have been around a long time and have been adapted to many applications. Differential pressure devices measure tank level based on the pressure difference between the bottom of the tank and the headspace in pressurized vessels or atmospheric pressure in vented tanks. They are among the easiest instruments to isolate from the process for maintenance and calibration. Radar gauges are among the most versatile at a price. Radar gauges come in two variations. Top-mounted non-contact radar gauges use an open beam reflected radar signal to determine liquid level. Guided wave radar devices, here on the right, are similar, but the radar signal follows a waveguide down to the material where the surface partly reflects the signal and allows level calculation. Laser level is a relatively uncommon technology that shows increasing promise for certain difficult applications. Laser level gauges are top-mounted, non-contact devices that project a laser beam toward the surface. Time of flight is used to calculate the distance of the material from the top of the tank. According to our chart, there isn't much that can't be done using nuclear level technology, providing you can justify the cost, which includes significant safety and regulatory concerns. Nuclear gauges infer level even in the harshest reactor conditions by passing radiation through a tank's walls and its contents to a detector on the opposite side. The radiation is attenuated in proportion to the amount of material traversed, which is correlated to the liquid level. There are other ways to measure level, such as weighing the vessel and its contents with load cells. In most applications, any one of several different level technologies could be made to meet the requirements. Often the deciding factor is the life cycle cost, which includes the costs of installation, maintenance, and calibration. Understanding all of the installation considerations at the start will keep a project from exceeding budget and help minimize headaches. So before any work is done, also answer these questions. What is the stilling well type and how will it impact the level transmitter choice? What are the process connection types and sizes? How will they affect the installation, including access for maintenance? How much modification will be required to the tank itself and what will that cost? What is the total cost of cabling, conduit, and/or wireless associated with the project? What auxiliary equipment will be needed, such as heaters, displays, and field modules, and what will those cost? Finally, weigh in the plant's ability and inclination to support and service the instrument. No installation will be successful without it. Studying these areas of the installation will help determine which level technology best suits an existing tank. When specifying a level transmitter, talk to the manufacturer to determine the installation requirements on each tank and make an informed decision on the installed costs of the system, not just the specifications of the level transmitter.
Thank you for watching part 1 of the Control Educational Video Series, Process Control Basics, Level Measurement. This video has been brought to you by our sponsors, VEGA, Endress Hauser, and KROHNE. More than 70,000 installations of VEGA 80 GHz radar have been made around the world for liquids and solid level measurement. The superior focus of VEGA 80 GHz sensors work around agitators and other obstructions. This instrument can store 250 events and 100,000 measured values with a real-time clock. Endress Hauser Micropilot FMR10 and FMR20 provide continuous, non-contact level measurement perfect for water, wastewater, and utility applications in all industries. They are the most compact, non-contact radar on the market with a Bluetooth commissioning, operation, and maintenance app. Simple, safe, and secure wireless remote access via Bluetooth works even in hazardous and difficult to access areas. KROHNE is a worldwide technological leader in the development, manufacture, and distribution of accurate, reliable, and cost-effective measuring instruments for the process industries.